So hi everyone, and welcome to the second seminar in the seminar series on theory of computing for fairness. Today we have Aaron Roth as our speaker, and Aaron Roth deserves no introduction. No, I'm just kidding. So Aaron is a professor of computer information science at UPenn right now. He's also part of the Warren Center for Network and Data Science, and he's also the co-director of the Network and Social Systems Engineering program at Penn. He's also right now on Amazon Scholar, and he's at Amazon AWS. And there are many other things I can tell you about Aaron. But so today, so Aaron is going to tell us about his work on online multivariate learning, means, moments, and prediction intervals. And so, Aaron, if you want to get started, please go for it. Oh, by the way, sorry, this is recorded, and if it would be amazing if everyone could mute themselves when they're not speaking or asking a question. Thanks. And so, Aaron, yeah, take it away.
Great, thanks, Juba. And this is joint work with a bunch of other excellent people, many of whom are also on the call: Varun, Chris, Georgie, and Malesh. Please interrupt me with questions. You know, the talk is going to be more fun if it's interactive. So, you know, if something's not clear, just you know, yell on out. So, at a high level, we have a pretty simple goal, basic goal, and one that is sort of not outwardly related to fairness. What we'd like to be able to do is we'd like to endow sequential predictions, you know, predictions that we have to make online as information comes in, with uncertainty estimates. We'd like to be able to know how sure we are about our predictions, and we'd like to do so by making no or minimal assumptions about the data. And let me start by you know, asking, like, what do or what should uncertainty estimates mean? And let's just to take a salient example, imagine that there's maybe a pandemic, so some rapidly changing situation. Patients are coming into the hospital, and what you'd like to do is you'd like to be able to look at their charts and make a prediction for what the estimated severity of their disease is going to be maybe in 2 days' time, so you can figure out who can be sent home and who needs more care. And so, you know, as a cartoon, you know, maybe a patient comes in, you look at their chart, and the doctor can say, well, you know, given your features, given what I know about you, I've got some model, and it predicts that the expected severity of your disease in 2 days' time is something, f of x. And the patient could ask, how sure are you? You know, this is an important thing that you're predicting. There's different things the doctor could say, but for example, what she might say is, I have a 95% prediction interval that the severity of your disease will be between some lower bound L of x and some upper bound U of x. And so the question is, okay, when the doctor says this, what does it mean? And what you might hope that it means, what it ideally means, is that what you're being told by the doctor really has to do with the conditional distribution on your label, the conditional distribution of your disease severity in 2 days' time, conditional on everything that's known about you, conditional on x. Okay, so hopefully f of x is like the expected value of your label conditional on x. And this prediction interval, what it means, hopefully, is that conditional on x over the sort of remaining randomness of y, this is somehow randomness over the unrealized or unmeasured randomness of the world, you know, the probability that your label, that your disease severity falls outside of this prediction interval is, say, exactly 95%. Right? It would be nice if these predictions meant this, because this would mean that you could really interpret these as predictions about you, and you could use them to make decisions. But this is not what they mean generally. We'll talk in a moment about why not. But more likely, what these are various flavors of marginal guarantees, which means that rather than averaging over the unrealized or unmeasured randomness of the world, conditional on features, what these are really doing is averaging over people. Okay, so probably more likely f of x is some calibrated predictor. We'll talk in much greater detail about what that is in a moment. And what marginal coverage means for a prediction interval is that if I average over all people, then for 95% of people, their label is contained within the interval. But even though these sort of expressions look similar, the semantics are quite different, right? This is an average over randomness pertaining only to you, and down here it's an average over people. And so I want to talk about two things. First, why you really can't hope for the thing in the orange box, and second, why you should not be satisfied with the thing in the blue box. And so first of all, like why can't we actually get these conditional guarantees? And if you think about it, they're sort of obviously too strong, right? Like in a rich feature space, I have probably seen nobody exactly like you before, meaning I haven't seen anyone with exactly your vector of features X before. And as a result, strictly speaking, I have no information at all about the conditional distribution on your label, conditional on your features, because this is a distribution I've seen like no samples from. And so without making some kind of heroic assumption, there's just no way that I can sort of promise that I've correctly estimated some quantity about this distribution that I've never seen before. And so I'd say in the literature, there are two standard solutions for dealing with this. And the first is to make these assumptions. Okay, so I could assume something about what the world looks like, right? I could assume, for example, this is what happens in the ordinary least squares model, that your conditional label expectation is actually some unknown linear function of your features. Okay, and then I could use, since everybody shares the same model, I could use data that I have about many people to estimate the parameters of the model, and I could turn that into like a true conditional prediction interval for you. But of course, this will be correct only if we believe the model, and especially when talking about individuals, we probably should not believe the model, even if the model is good in aggregate at making predictions. The second, and I think I hear what are probably very cute kids in the background, but if someone could mute their microphone, that would be great.
Oh, I was thinking that was you, Aaron.
Yeah.
Yes, same, but everyone please mute yourselves if you are not muted right now, thank you.
Yeah, they sound cute. The second standard solution is to do what we've just discussed and sort of give up on these conditional guarantees and move to marginal guarantees. And this is what's done when people talk about calibration. This is also what's done when people talk about conformal prediction for coming up with prediction intervals, if you've heard of that before. So why shouldn't we be happy with marginal guarantees? And let's go back to our little cartoon example. So again, remember the doctor has told you that you've got some 95% marginal prediction interval. And you might think to yourself, okay, well, I'm part of some demographic group representing less than 5% of the population, say, so what does this marginal prediction interval mean for me? And the answer is it means like, possibly like literally nothing, because it is consistent with the guarantee of a 95% marginal prediction interval that for people from your demographic group, their label falls outside of the interval 100% of the time, right? Because the promise of a marginal prediction interval is just that it correctly covers the label for 95% of people. But if your demographic group represents less than 5% of the population, it might never cover people in your group. So, like you don't have to do just one study, right? So you could ask the doctor, what about for people like me? And she could, flip through her medical journal and say, okay, well, for African Americans under the age of 50, the 95% prediction interval is from A to B. For women with a family history of diabetes, the 95% prediction interval is from C to D. For people with egg allergies and no history of smoking, the 95% prediction interval is from E to F. But the problem is you might be a member of all of these demographic groups. And it is, again, consistent with the guarantee of marginal prediction that, for example, these prediction intervals are disjoint. Okay, so there's no clear way for how you can sort of combine information of this sort that is estimated marginally for different groups, even if you are a member of all of them. Okay, so that's why you might not like marginal coverage guarantees. Now there's this sort of large literature on what's called conformal prediction, which in an online setting, so data arrives one piece at a time and you have to make these predictions, gives marginal coverage guarantees. But this literature also makes strong assumptions about the data. In particular, it makes sort of assumptions that are kind of standard in lots of machine learning, which is that the future should look like the past. And so formally, what it assumes is that the data is exchangeable. So the data distribution should be invariant to permutation. So for example, IID data would satisfy this. But often this isn't true. So for example, covariate shift would violate this assumption. So in our pandemic example, as the disease moves through the population, the demographic of patients who show up at your hospital can change suddenly and dramatically. Label shift, so as treatments improve, for example, the conditional distribution on Y given X might change. Strategic effects, like suppose we're talking about predictions on lending or hiring setting. Well, people might manipulate their features to sort of try to gain what they want from your deployed classifier. You might, as a result, retrain your classifier. Doing this will change what the distribution looks like and make it non-exchangeable. And you might just be trying to predict something that is like inherently non-exchangeable, like time series data, right? So if I'm trying to predict the disease severity by time, this looks very different if I sort of randomly permute the days. And so at a high level, and now I'll sort of dive into definitions, in this work, what we're trying to do is mitigate both of these problems for sequential prediction. So we want to both make stronger than marginal guarantees, and we want to assume nothing about the data. We want to work in a sort of online adversarial setting. And we're going to do this for prediction intervals, and that's what I'm going to spend a bunch of the time focused on. We'll also do it for means, which is going to correspond to multi-calibration, which I'll remind you of in a moment. And we can do it for higher moments like variances of the data distribution. I'm not going to talk about that because we have a talk by Chris next week, sort of entirely focused on how you apply things to moments. And as you'll see, the sort of techniques we develop are actually quite general. So these are the three distributional properties that we sort of decided to focus on. But if your favorite distributional quantity is not on this list, I think it's quite likely, and we'll see as we see what the solution looks like, that similar techniques can be used to predict that distributional quantity. Okay. So let me start by telling you about mean multi-calibration, which is an elegant idea proposed a few years ago by people who are central to this center for dealing with this problem of marginal prediction for means. Right, so this problem of marginal guarantees, I discussed it in the context of prediction intervals, but it's a problem already just when we're talking about means, right? If I predict some expected disease severity, but really it's an average over people, then it might have very little to do with you or people from your demographic group if your demographic group represents a small part of the population. And multi-calibration, which is this nice idea by Hebert Johnson, Kim, Reingold, and Rothblum, addresses this. So let me start by telling you what multi-calibration is. And I'm going to tell it to you in the context of online prediction. So the definitions are like a little bit different if you're used to looking at this, like say in the original paper, which was for batch prediction. And I'm also describing them in a differently parameterized way. But these are basically the same definitions in the sense that if you apply these to a batch setting and set the parameters appropriately, you recover the guarantees from the original paper. Okay, so we're talking about sort of a sequential setting. So I will make no reference to a distribution. Instead, what you have at hand is a sequence of examples that you will have seen one at a time. Okay, let's call them x1, y1 through xt, yt, where x is some vector of features in some abstract feature space, and y is a label that, for the purposes of this talk, think about as being a real number between 0 and 1. And you will have made a sequence of predictions, which I'll call y bar, at each time step, which also will be numbers between 0 and 1. And there's two quantities I want to talk about that I'll call mu of s and mu bar of s. So here s will be some subset of the feature space. So maybe think about s as being the set of all features describing people in some demographic group. So mu of S is just going to be the sum of the realized labels, like the true realized labels over time for people who fell into demographic group S. And mu bar of S is just the sum of our predictions for the same set of people. So mu bar of S is the sum of our predictions, Y bar, for all of those individuals whose features put them in demographic group S. Okay, and we'll say that our predictions were mean consistent on this set S if these two quantities take the same value. Like ideally, when I average over all of the predictions that I've made and over all of the labels that were realized, they're the same. And more generally, we're going to have to talk about approximation error. So let's say that they are alpha mean consistent if these two quantities differ by alpha t. And let me just sort of make a remark here about the normalization. So it might be, you might think it's sort of more natural to write alpha s here rather than alpha t, because if I viewed these as means, I'd want to divide by the size of the set. And that's true, indeed you would. But it's going to be necessary to basically give weaker guarantees for smaller sets. Think about this in the batch setting. The online setting is only harder. If there's some group that's very small, I've seen very few samples from them, it's just not going to be possible in a statistical sense to say anything about the average of their labels. And so we're going to have to settle for guarantees that sort of get weaker for smaller sets. And this parameterization is one way to sort of smoothly do that. So we're going to give algorithms that are able to bound alpha. We'll be able to take alpha to be quite small, but this is sort of saying our guarantees will get sort of weaker at a linear rate in the size of your group. Okay, so that's mean consistency. And now let me tell you what calibration means. And so to talk about calibration, we have to talk about a discretization parameter. Okay, so in some papers on calibration, we talk about algorithms that actually make predictions only in a discrete grid. We're going to talk about algorithms that can make, like real valued predictions, but still we have to talk about this discrete grid. So given a discretization parameter m, the discrete grid that we're talking about here is just the set of 1 over m many points, 1 over m plus 1 many points that corresponds to, like 0, 1 over m, 2 over m, so on and so forth. And for each grid point, I'm going to talk about a bucket, which basically is going to contain all of the points that are closer to that grid point than to any other. Okay, so if I say that some prediction y hat is in bucket I, what that means is that y hat is closer to I over m, like grid point I, than it is to any other grid point. Okay, and one more piece of notation. Given some subset of the feature space, given some demographic group, S of I will correspond to all of the people from that demographic group that I've seen in this sequence for whom my prediction was in bucket I. Okay, and with those definitions in hand, we can say that a sequence of predictions is calibrated, and this comes with two parameters, alpha and m, alpha m calibrated, if for every bucket, we satisfy mean consistency, alpha mean consistency, on the set of all points for which our predictions were in bucket I. Okay, so sort of canonically, this is often talked about in terms of like weather prediction, in which case what it means is if I'm a weather forecaster, it should be that if I look at all of the days on which I predicted a 10% chance of rain, it should have rained 10% of the time. If I look at all of the days on which I predicted a 20% chance of rain, it should have rained 20% of the time. And then multi-calibration just asks for calibration, not just overall, but simultaneously on all of these, simultaneously basically on some possibly enormous collection of overlapping demographic groups. Okay, so multi-calibration is parameterized by some collection of groups, some collection of demographic groups if you want. They can be intersecting, it can be a very large set. And we say that a sequence of predictions is alpha m multi-calibrated with respect to this collection of demographic groups G, if basically it is calibrated not just overall, but also on every subsequence corresponding to days on which people from group G arrived. Okay, So that's multi-calibration. Very nice definition. And when you see this definition, you sort of realize, okay, like this is sort of the special case of means, but for any distributional estimate, I can sort of ask for like the multi-valid analog of the same thing. So let's just do the same thing for prediction intervals. So given a sequence of examples of the same form, so every day I see some feature vector and some label, I will have made a sequence of predicted prediction intervals, which are now intervals. So every day the prediction that I've made is corresponds to like a pair of numbers between 0 and 1 that are like the left endpoint and the right endpoint of the interval. And we're going to have to talk about a bucketing once again. So let's say that a particular interval is in bucket ij if the left-hand side of the interval is in bucket I and the right-hand side of the interval is in bucket j. Then we will say that a sequence of prediction intervals is alpha m multi-valid for some coverage target, like 95%, and some collection of demographic groups G, if simultaneously for every bucket of prediction intervals and for every demographic group, if I look at the sum of all of the days in which I have made a prediction, in which I've made a prediction interval that falls into bucket ij, and in which the person who showed up that day was in demographic group S, and I look at the fraction of those days in which my interval actually covered the label, that fraction should be 95% if I want a 95% prediction interval, or it should be 90% if I want a 90% prediction interval. And more generally, using the same sort of relaxation for the same way of measuring approximation, I'll say it's an alpha m multi-valid sequence of predictions if this difference, which like should be 0, is maybe not 0, but at least bounded by alpha times t. Okay, so it's again asking for the thing that we wanted, that the prediction interval should cover, say, 95% of the labels, both not too many and not too few, but I'm asking for it now conditional on two things. Conditional on the actual like bucket in which the prediction interval falls into, so it's got a calibration-like flavor, and also conditional on the individual falling into some demographic group. Okay, so this is sort of the natural analog of multi-calibration for prediction intervals. And finally, before I tell you how to start deriving some results, let me just remind you of what the online problem is, because we're going to be thinking about sort of an adversarial online learning setting. And so what happens is the following. There's going to be some sequence of days, capital T. And every day, some adversary who could be adaptive and who could know, for example, exactly what algorithm you're using is going to select two things. They're going to select a feature vector, and they're also going to select a label. And they're going to show the feature vector to the learner. So the learner will see xt before he has to make a prediction, but of course he won't show the label to the learner. The learner is trying to predict something about the label. And then the learner will get, seeing the feature vector, having the feature vector in hand, will have to make some prediction. And the learner is going to be allowed to flip coins. In fact, in an adversarial setting, it's going to be necessary that the learner is randomized. And the learner will make some prediction. Okay, the prediction could be of the form of a mean if we want multi-calibration. It could be of the form of a prediction interval if we want multi-validity. It could be a variance or some other higher moment that Chris will tell you about next week. And after this prediction is made, the learner gets to observe the label. Okay, and then can sort of update his state as a function of that, because the label sort of tells him something about how well he did today. And the goal is to design some algorithm that can guarantee that against a worst case sequence of examples, against a worst case adversary, that at least if T is large enough, the sequence of predictions satisfies multi-calibration or multi-validity, or your favorite notion, your favorite sort of notion of multi faithfulness to this distributional quantity that you're trying to predict. Okay.
Hey, Aaron.
Yes.
Could you go back to the definition of multi-validity? Yeah, perfect.
Yeah, there we are.
So I'm trying to parse where the absolute values are and why this makes sense.
I may have put the absolute values in the wrong place. Yes, you're right. So the absolute values are in the wrong place. It would not make sense as I've written it. I want the absolute values to be outside the sum, because what I want is that if I sum over all of the days in the
this would be
I want basically
too
the
strong
fraction
of a guarantee.
Exactly, you couldn't satisfy this. What I want is that, especially since like this is a indicator, right? So it's going to be 1 or 0. So this is like ridiculous. So good eye. The absolute values should be outside. And so what this should say is that averaging over the appropriate sort of tranche of examples, the fraction of times that I cover the label should be 95%.
And you actually do want the absolute value here, as opposed to just sort of saying.
I don't want it to be either too big or too small. Like if I didn't have any absolute values, there'd be sort of like a trivial solution, which would be to just always predict like the whole interval, and like lo and behold, like you always cover the label, well, 100% of times, which is even better. I don't want that trivial solution. So when I ask for 95% prediction intervals, like I really want 95%, like 96% is no good.
And also 80% is no good.
And also 80% is no good. I'm aiming for the target 95%. I don't want to overshoot or undershoot.
Great, thanks.
Aaron, while we're on this slide, so is it clear that without making any assumptions on the data, this is always feasible?
We will talk about exactly this. So there is going to be a mild assumption we're going to have to make. I'll tell you what it is, and we'll discuss, whether it's mild or not.
Cool.
But yeah, like as written, if you make no assumptions about the distribution, even in a distributional setting, even if you know what the distribution is, you can't achieve this. For example, I might have like just a point mass, and then you can't get 95% coverage. You have to get 100% or 0%. So basically, we're going to have to assume that it's not a point mass.
Aaron, do you want t on the left-hand side? You want the fraction of times you follow?
You can divide by t if you want on both sides.
But 1 minus delta would be also divided by t.
Oh, let's see. I think this is not how we write it in the paper, so it's possible there's an error here. But I think this is right in the sense that this is a sum.
If the 1 minus delta is in the summation.
Yeah, it is in the sum.
The 1 minus delta is in the summation. Exactly.
Oh, okay, makes sense.
Yeah. Okay. Good. Does the definition now like parse and make sense to anyone? To everyone? Apologies for putting the absolute values in the wrong place. Okay. So let me, even though sort of I think the headline result here is for prediction intervals and more generally uncertainty prediction, let me walk you through how you derive an online algorithm for mean multi-calibration, because I think this is the simplest case, and basically once you know how to do this, you know how to derive an online algorithm for any kind of multi-validity for any kind of distributional property. So let's start here and then see how far we can push it. Okay, so I want to write down some quantity that's going to correspond to the sort of part of my multi-calibration error that corresponds to a particular demographic group S and a particular bucket I. Okay, so let's call this quantity VSI. And I realize now that I use S 2 times to mean 2 different things, but this is for a particular demographic group and a particular bucket, and it's like my multi-calibration error for this demographic group and this bucket from days 1 up through day little s. And this is just the sum over all of the days of the indicator for whether I care about this day, right? For this particular demographic group S and this particular bucket I, which is just the indicator of whether the person who arrived at day T is in demographic group S and that the prediction I made at day T is in bucket I, of the difference between the prediction I made and the actual like realized label. Okay, so I'd be like perfectly calibrated if all of these sums were exactly equal to 0. Okay, and to the extent that these things are bigger than 0 or less than 0, I am not calibrated. And so in particular, the way I've defined everything, if at the end of time, if at the end of t days, I can guarantee that the average of all of these quantities, for all demographic groups S and for all bucket indices I, is less than alpha, then I will be alpha M multi-calibrated. So sort of just by definition, like I wrote this quantity down so that that would be true.
And Aaron, just to make sure, so this G is once again to the power of your universe, right? So it's every possible subgroup.
It's a subset of that. So G is the set of all demographic groups that you care about.
That you care about, okay.
It's not absolutely everything, probably, but it can be big. We're going to have some log G dependence. Okay. Okay, and so here's the basic idea. I learned about this idea while reading through old economics papers. It's like a good idea. They have a lot of good ideas in there. And so this is, a generalization of an idea that showed up in a short paper by Freudenberg and Levine back in 1995. And I think it's extremely useful, so let me tell you about it. So what do we want to do, right? We want to guarantee that the maximum over all demographic groups I over all demographic groups S and buckets I, the maximum absolute value of these V quantities is small, right? Because the way we've set things up is that if at the end of capital T days, the maximum of these absolute values is small, then we will be multi-calibrated. But the maximum is sort of not a nice analytic function. And so the first thing we're going to do is we're going to sort of approximate this maximum with a more well-behaved function, some smooth differentiable function that has a nice Taylor expansion. And we're going to use the obvious one, right? We want to bound a maximum, so we're going to use what is called in machine learning a softmax function, which is just the sum of the, so rather than taking the maximum of all of the groups, what I'm going to do is I'm going to sum over all of the groups, but I'm going to take the sum of the exponential, okay? And I want to bound not just the maximum of all of the V quantities, I want to bound the maximum of the absolute value of all of the V quantities. And so I'm going to sum for every bucket I and group S of both the exponential of the V quantity and the exponential of the minus V quantity to sort of bound that. I want this to be able to bound the absolute values. So I don't want these things to be either too big or too small. And there's some eta parameter here, which I'm going to set later. But just to sort of observe that this is a reasonable thing to do, what you can sort of immediately note if you think about it is that, first of all, if I can bound the surrogate loss, then I also bound what I want. Because if I take the log of this surrogate loss and divide by eta, that is an upper bound on the quantity that I want, on the maximum of all of these V's. And also, I haven't overshot too much, right? If I take the log and divide by eta, then I am no more than the quantity I wanted to bound plus something that looks like log of the number of groups divided by eta. Okay, so bounding this surrogate is like a reasonable thing to do. And then the other simplification I want to make is, it's kind of hard to bound this thing, right? This is some function of the entire history of interaction between the learner and the adversary. So instead, what we're going to try to do is greedily bound, we're going to take a greedy approach that, cross our fingers, hope it'll work. What we're going to try to do is argue that, even if we don't think any more into the future than, one day at a time, we take the past as given, we wait until we've seen today's feature vector X, that what I can do is bound the expected increase of this quantity for one day. So what I want to do is conditional on the whole history so far, which in particular determines what the adversary is going to do tomorrow, conditional on the X, which I've seen. I want to think about what the expected increase in this surrogate loss function is, the one-day expected increase, so the difference between LT and LT minus 1, as a function of the prediction that I can make. Okay, and the idea is if I can show that there's some way of choosing predictions so that at every round for every history, this expected one round increase can be made to be small, then I will get a bound on the final surrogate loss just by summing them all up and telescoping. Okay, so that's going to be the basic idea. Okay. So here's a lemma that is easy to prove and state. Don't worry too much about the notation. So remember this delta quantity. What is this delta quantity? It's the expected increase in the loss function from day t-1 to day t. Okay, and it's conditional on the history so far. So in particular, it has fixed a distribution on the label, because fixing the history fixes the adversary's label distribution. And what we're going to do is we're basically going to take like a first order approximation of this thing. This is why it was nice to use this softmax instead of a max. There's like a nice Taylor series expansion for an exponential. So we're going to take a first order approximation of this thing and upper bound it by something that looks like eta times a linear term, right? The expected value of the label tomorrow minus our prediction tomorrow, okay? Times something, times some constant that for now you don't have to worry about what it is, but it'll become relevant in the algorithm what it is. This is some constant that depends on the point that showed up today, depends on xt, and just corresponds to the sum of the exponentials of our sort of calibration losses so far up through today. Not summing over all of the demographic groups, but only summing over the demographic groups in which today's individual appears. Okay, so that's implicitly introducing a new piece of notation here. So when I write g of xt, what I mean is the set of demographic groups for which xt is a member. Okay, so looking at this, think about, so the end here, this is literally just some constant that is entirely independent of anything, x and y. The beginning, the important thing about this is that it's linear. It's the difference between the expected value of tomorrow's label and our prediction. And this c thing, this is a constant that depends on the data point that showed up today. In particular, it's some sum over the demographic groups for which xt is a member. And this is just like a first order approximation. So you can prove this for yourself. Basically, you write out this difference, you distribute the expectations correctly, and then you remember that you can approximate e to the x by 1 plus x plus 2x squared, so long as the absolute value of x is not too big. And it will be, because we're going to choose eta to be something that's less than 1/2 in the end. Okay, so this is just some simple, like algebraic approximation, nothing deep going on here. Okay, and let me now take a brief interlude to remind you about zero-sum games, which are going to form an important part of the next step of the analysis. So a zero-sum game is defined by 3 things. So we have a minimization player who's got some finite strategy space A1. And just to foreshadow, we're going to identify the minimization player in some game with the learner. We've got a maximization player who's got some other finite strategy space A2. We will identify him with the adversary. And we've got some real valued utility function which takes as input an action from both of the players and spits out a real number. And this utility function is extended to distributions in the natural way. If the learner is playing some distribution over actions and the adversary is playing some distribution over actions, the utility function applied to those distributions is just the expected value of the utility function when we sample actions from those distributions. And the one thing you need to know about zero-sum games is that the order of play doesn't matter. This is von Neumann's min-max theorem. So just parsing this out. If the learner first has to commit to some distribution over actions, and then the adversary gets to examine that distribution and pick the absolute worst action, okay, then we would get some value of this game. Alternately, if the adversary first had to commit to some distribution over actions, and then the learner got to examine that distribution and then pick the absolute best action, we'd get some other utility value. And the min-max theorem says both of these are the same. The order of play doesn't matter. And this is going to be relevant for us because sort of the world in which we actually want our algorithm to live is on the left. Right? Like the algorithm is going to have to be some object we commit to, and it's going to have to have guarantees against a worst case adversary. So in particular, like we really do have to commit to some algorithm, which will specify in particular a distribution over predictions that we make at every round. And then the adversary could pick the absolute worst thing every day. On the other hand, it's going to be a lot easier to think about how to do well on the right-hand side here if the adversary first commits to a distribution, because once I know what the distribution is, it's very easy to make predictions, right? It's easier to predict something you already know than something you don't know. That's going to be the idea. And so here's what we're going to do. We're going to define a zero-sum game. And remember, what we want to do is we want to prove that we can guarantee that at every round, our increase in our surrogate loss is small. Okay, so let's just define a zero-sum game in which the utility function is exactly the upper bound we proved on the increase in our surrogate loss. Now, we need a finite strategy space for both players. Now, the nice thing about this utility function is that, well, it is linear in the adversary's action. It is linear in the realized label. Okay, and so what that means is that for any distribution on labels, our utility depends only on the expectation of the label. And so without loss of generality, we can take the adversary's strategy space to be just like binary labels, 0 or 1, because I can realize any expected value by just randomizing over the endpoints of the interval. Things are more complicated for the learner, right? Because the strategy space, the utility function is not linear in the prediction of the learner. This part is, we have, a dependence on our prediction in this linear term, but the constant that is multiplied here depends on what bucket our prediction falls into. So this is some, annoying like discontinuous function in the strategy space of the learner. And so, we'd like the strategy space for the learner to be sort of the full, real valued interval, but then the min-max theorem wouldn't apply. So instead we have to take some discretization of the strategy space for the learner. And we will have a discretization parameter R. And so we'll imagine the strategy space for the learner is, the set of all points 0, 1 over Rm, 2 over Rm, etc. But what I want you to sort of note, or just sort of keep in mind now, is that R is sort of a nuisance parameter for us. It's not going to show up in the running time, and making it bigger will only help our bounds. So we just need some discretization to make the min-max theorem apply. So really think about R as being as large as you want, like arbitrarily large. Okay, so this is morally the continuous interval, but for the really there is some discretization. It's just very fine. Okay. So we've got this game and we know the min-max theorem. So let's now bound the value of the game in the easy case, in which we imagine the adversary goes first and commits to some distribution. Okay, so the adversary first tells us what their label distribution is. Okay, and then we have to pick the prediction that minimizes this expression given the label distribution. And now this is like kind of easy, right? Because we know what the expected value of y is because the adversary just told us. And so what we'd really like to do is just to make our prediction exactly equal to the expected value of y, right? Which would just sort of zero out this term. It would zero out almost all of this expression. Now we can't quite do that because of our discretization, but we can almost do it, right? So we can always choose our prediction to be the closest discrete point to the expected label of the adversary, which means that, and given our discretization, that means we will be within plus or minus 1 over Rm. And so we can make this term as small as 1 over Rm, and we can observe that this term, this constant here is no bigger than the whole loss function. And so what we can observe is that the value of the game is a small multiplicative factor of the loss that that has been accrued to the algorithm so far. Eta is a parameter we get to set, R is a parameter we get to set, so we can make this quite small. And then, this is a zero-sum game. We can apply the min-max theorem to sort of, the nice thing is it's sort of easy to figure out what you should do if the adversary tells you what the label distribution is, right? Like he tells you a distribution and then says, predict the mean. But what the min-max theorem tells us is that there must therefore be some distribution on actions we could have played that we could commit to first, meaning some algorithm out there that we could have committed to, such that no matter what the adversary did, like against any adversary, it would guarantee that our expected increase in loss was no more than the same quantity, the same upper bound we proved in this much more well-behaved world in which the adversary goes first. We're really sort of using the min-max theorem to great advantage here. But of course, this is a non-constructive argument because the min-max theorem doesn't tell us what that distribution is. Okay, but let's derive the bound first, and then let's worry about the algorithm. So what we have observed by applying the min-max theorem is that for every adversary and for every history and for every round T, the learner has some distribution over their actions, over their discrete set of predictions that guarantees that the expected loss at day T is no more than the loss at day T minus 1 times this multiplicative factor. And we know that the loss at day 0, when all of these V quantities are 0, so the E to the V quantities are 1, the loss at day 0, which is a sum over all of the demographic groups and buckets, is just 2 times the number of demographic groups times the number of buckets. Starting with sort of this base case, we can just telescope and note that our expected loss at day T has this simple bound. Our initial expected loss times the multiplicative factor by which it increases at every round raised to the Tth power. And recalling that the quantity that we want to bound, which will in the end bound our multi-calibration error, is bounded by the log of this surrogate loss function, we immediately get the following theorem, that there is some algorithm, we don't know what it looks like yet because we argued for it non-constructively, but there's some algorithm that against any adversary guarantees alpha m multi-calibration with this bound. And remember, R here, we can pick it to be whatever we like. So in particular, you should read this bound as 2 plus epsilon for an arbitrarily small epsilon times the square root of the log of the number of groups over T. And there's a sort of analogous high probability bound. Okay, so I want to spend a few minutes telling you about prediction intervals. So I'm not gonna, there's another step here for calibration, which is we have just argued existentially for the existence of an algorithm that has these nice multi-calibration bounds online, but we haven't seen the algorithm yet. And there's some, there's some doing to get the algorithm, but in some sense, all of the room for creativity has already occurred in the sense that what the doing is it's just computing the min-max equilibrium for the game that we've defined, right? We know the strategy that guarantees that the bound we just proved is just at every round the learner should play according to the equilibrium of the game we defined. And it turns out you can compute that. And for the case of multi-calibration, it's actually an extremely simple algorithm. Let me just tell you about it real quick. So every day, person T shows up. We know what their demographic features are. We know what their features look like. And so for each of the M buckets, we can compute this constant Ci, which is again, just the sum of all of the groups for which today's person is a member of the exponential of these V functions. And there's 3 cases. It might be that all of these constants are positive, in which case you just predict 1. It might be that all of these constants are negative, in which case you just predict 0. And in the only remaining case, there must be 2 adjacent buckets, right? I star and I star plus 1, so that these constants have opposite signs. And in that case, what you're going to do is you're going to find a pair of these adjacent buckets, and you're just going to randomize between them so that the expected value of these constants, one of which has negative sign and one of which has positive sign, is exactly 0. And what you're going to do is you're going to try to predict the 2 points that are closest together in these buckets up to your discretization. So if you pick bucket I star, you're going to predict I star over M, like the upper boundary, minus 1 over Rm. Otherwise, you'll predict I star over M. So there's a little bit of randomization here, but it's actually like quite minimal in that you're randomizing between 2 points that are almost right next to each other. And just observing the running time, this is sort of a very simple algorithm, right? The running time is just like linear in the number of buckets once these quantities C are computed. If your number of groups is very large, almost all of the computational cost comes from computing these constants, because these are sums over the demographic groups for which the person today is a member. And so in the worst case, this is linear in the number of groups, but actually it's actually only linear in the number of groups that today's individual is a member of. So you can get reasonable runtime even if there's lots of groups, so long as you have the promise that nobody is a member of more groups than you can enumerate. Okay. So in the remaining, like 6 minutes, let me tell you about prediction intervals, but it's actually going to be pretty easy because this strategy that we just went through for mean calibration applies, it's extremely general, right? It applies to all sorts of things. So let's just instantiate it for prediction intervals. So we're going to redefine the measure of error for each demographic group and for each bucket to correspond to what we want. So to correspond to multi-validity now. And so each of these V's, now parameterized by a demographic group and a bucket in which an interval might fall, is just the sum over all of the days in which the person who showed up was a member of that demographic group and in which the predicted bucket was, the predicted interval fell in bucket ij, of the difference between the indicator that the interval covered the label and your target coverage, like 95%. And once again, we will be, alpha multi-valid if we can guarantee that at the end of the interaction, the average of all of these quantities is bounded by alpha. We're going to use exactly the same surrogate as before because we want to bound a max, so it makes sense to still use a softmax surrogate. And we're going to prove basically the analogous first order approximation to the increase in our surrogate loss, which is sort of something that looks extremely similar to what we saw before. The linear term now corresponds to the quantity that we care about for multi-validity, which is the difference between the expected coverage of our interval and our target, 95%. Okay, and we'll define the game the same way as before. The strategy space for the learner is now intervals instead of predictions. We'll do a similar discretization. So the strategy space for the learner is the set of all pairs of points in our sort of discrete set. The utility function corresponds to our upper bound that we proved on the increase in the surrogate loss. And there's now a question we have to answer, which is, what is the strategy space for the adversary? And remember what we need to do. What we need to be able to do is we need to be able to bound the value of the game when the adversary has told us the distribution, right? So we need to be able to, like, given a fixed distribution, argue that there is some interval that will get approximately the right coverage. Okay. And what you might note at this point is that even for a known distribution, that's not always possible, right? Consider like a point mass, in which case, my choices are to like cover the label 100% of the time or like 0% of the time, both of which will be bounded away from 95%. Okay, so what I'm now going to do is enunciate an assumption that will make this possible and then argue that this assumption is reasonable. Okay, so let's say that a label distribution is rho Rm smooth if for every interval that I might pick that has width less than 1 over Rm, the probability mass of that interval is less than rho. So I'm just asking that the distribution not be too concentrated on any interval that is like too small. And so of course this becomes a more mild condition the larger I make R. Okay, so let's work things out for quickly under this assumption, and then let's sort of argue that this assumption isn't crazy. So under this assumption that the adversary is always going to play a label distribution that is rho RM smooth, we can again bound the value of the game, because for any fixed rho RM smooth distribution, I can now just read off from its CDF a prediction interval whose coverage differs from the target from 95% by at most rho. And so once again, I can obtain this lemma that says, existentially, there exists a distribution, an algorithm for the learner that they can play at every round that guarantees that the increase in this surrogate loss is small, where small is in terms of rho. And mechanically, with sort of the same analysis that we've already talked through, that gives an existential theorem. There is some algorithm for making multi-valid predictions that guarantees either an expectation or with high probability that your multi-validity error alpha is no more than, okay, this rate that we've seen before, like log the number of groups divided by t under a square root, plus rho. Right? Somehow, even for a single round, you can't guarantee to do better than rho. And so for this to be, if you wanted this rho to go away, you'd really need to assume that rho was sort of on the order of 1 over root t. Okay, so first of all, is this a reasonable assumption? So first, I would argue that it may well be a reasonable assumption if you're not really thinking about playing against an adversary, but just thinking about playing in an environment in which the distribution might change quite rapidly. Because as you make R very, very large, this is basically the assumption that the distribution just doesn't have point masses in any single spot. A continuous CDF will be, a continuous distribution will be rho RM smooth for large enough R. But more to the point, in an adversarial setting, we can actually enforce this. We don't have to assume it, we can enforce it as follows. So given, say the adversary gives us their label Y, what we can do is we can feed to our algorithm a label that has been perturbed by just a smidgen, right? We can add sort of uniform noise between minus epsilon and epsilon to the label. And by construction, the distribution that we are feeding to the algorithm will now be smooth. And in particular, if we want to make the rho term a low order term, we can choose R appropriately polynomially large, and we get a convergence bound that looks like what we want, log of G over T. Now, of course, the prediction intervals that our algorithm gives are only going to be multi-valid for the perturbed labels, not for the original labels, but they remain conservative for the original labels if you just expand them on both sides by epsilon. And in our algorithm, we're going to get runtime that's polynomial in epsilon, and so you can take epsilon polynomially small. So without any assumptions at all, you can get these sort of valid intervals that are sort of potentially too wide by only epsilon on either end, where epsilon is as small as you like. Okay, and I'm out of time, so I want to wrap up now, being mindful of that. But let me just point out that once again, we've given a non-constructive argument that there exists an algorithm that has this nice property, and our hands are sort of tied to come up with the algorithm. There's only one thing we can do, it's compute the equilibrium of this game. And we can do that basically by solving a linear program. It is some linear program that has not very many variables. It's got basically one variable for every prediction interval in the discrete range of the learner. So polynomially many variables in the parameters we care about, but it's got a lot of constraints. It's got a constraint for every smooth distribution, of which there are naively infinitely many, and you can argue you actually only have to care about exponentially many of them. But they're sort of constraints of a nice form. In particular, given a distribution, finding a constraint that is violated turns out to correspond to solving some fractional knapsack problem, so you can do it quickly. And so the algorithm in the end looks like the following. Every day, we see the point that arrives. We once again compute these C quantities, which should be familiar. They depend on the groups for which today's individual is a member. And with those quantities in hand, we solve a linear program, which gives us a distribution over prediction intervals, which we then sample from. Okay, so once again, if the set of groups is large, it's not solving the linear program that's the hard thing. It's computing these constants C, because you have to enumerate all of the groups for which an individual is a member. But if individuals are not a member of that many groups, then this is polynomial runtime, and runtime at worst linear in the number of groups you care about. Okay, so that's it. Thank you for listening. The paper is on archive.
Thanks, Aaron, for the talk. So we are already out of time, so let's maybe keep it to just one question if anyone has a question. And if you want to forward questions offline to Aaron later on, just please email me or Said and we can do this.
All right, well, thanks everyone for listening despite me going over time.
Well, that was a really good talk. So thanks for coming and giving the talk.